roll. All right, this is a lot of brand new information, so you need to be listening. You have never had this stuff before. Boys, be quiet. You have never had this before. We are starting the chapter on derivatives. Write this down. Derivative. Okay, I think I've talked about this last chapter just briefly, but here's what a derivative is, okay? There are many different applications for a derivative, but for this section or this chapter, a derivative is going to represent a slope of a tangent line, okay? Also, a derivative could be representing like a velocity, okay? A second derivative, I'm going to put second derivative, is a lot of times used to represent acceleration, okay? That's what we use second derivatives for, is for acceleration of things, okay? Slope of tangent line, velocity, also, the last one, is something called instantaneous rate of change. Also, instantaneous rate of change. That is what a derivative is useful for. So, for example, I'm just going to briefly go over a problem here. Let's say that I am starting
acceleration. That's physics.
Let's say I am starting.
Actually, I would never know.
To blow up a.
No. Let's say I'm doing a.
I didn't think I wanted to go into engineering.
I'm dropping a rock or something. Okay, we did this in trig. Okay, so let's say the height of my rock. Actually, let's say I'm kicking a rock up. So let's say we're doing something like this, right? Okay. Okay, so the height of the rock is starting in the air, like I'm tossing it up in the air and it's coming down and it's landing on the ground. Okay, so this axis is time and the other axis is height, right? So I'm taking a rock, I'm throwing it from arm level up and coming back down, right? Okay, so height is that, right? What I could do is I could look at from here to here and figure out the time and the distance it has traveled to do the average rate of change, right? Okay. On average, it's gone a time of this and a height of this, so I could figure out the average rate of change from start to finish. But the problem is, I want to know at this very instant when it is 3 seconds into its travel, what is that instantaneous rate of change? What is the instantaneous velocity at that point? I don't want to know the average over the course of its travel. I want to know at this very instant what is the speed at which it's going. And that is what a derivative is. So if we're given an equation for this, which is the equations that we were doing in trig this morning, the negative 16, t squared, whatever. Okay, we could use that equation to figure out instantaneous rate of change. It is going to be a derivative of that very point. We would plug in the second that we want and figure out that instantaneous rate of change, okay? So derivatives, there's lots of different meanings for them. They all kind of resemble the same thing, but slopes of tangent lines, velocity, instantaneous rate of change, second derivatives we'll do later on, but that's acceleration. We could even do third derivatives, fourth derivatives, that type of thing. But here we go, okay? So this guy, there's a real world application they start us off with in this section, which talks about the fact that derivatives are in use or that calculus exists in general is that it involves changing quantities, okay? So we know that if we're going 60 miles an hour for 3 hours, typically we go 180 miles, but that's not exactly true because we don't.
From the graph?
No. So other math. Okay, good question. Other math problems will say you're going 60 miles per hour for 3 hours, right? Okay. How much distance have you gone, right? Well, the max is 180 miles, right? But probably not because there might have been some starts and stops in there. I wasn't instantly going 60 miles an hour when I jumped in that car, right? Okay. Right. So that's the difference. 60 would be my average rate of change, okay? We want to know instantaneous rate of change, which may differentiate over the course of my travel, right? So average rate of change is 60. Instantaneous rate of change may be different at particular points. So that's the difference between a derivative and what you've learned in most math classes, okay? So there we go. All right. Here we go. Here's a curve, not unlike the one that I just gave you where I had the rock scenario. You guys got to listen. We've never done this before. Be quiet. Here's my rock example. So starting at point P, let's say I want to know the instantaneous rate of change of this guy. Okay? Whoa. I want to know the instantaneous rate of change. Rate of change. Okay? Now, instantaneous rate of change, another way of saying that is like the slope of the tangent line, right? So if I have this guy right here, I want to know his slope. And the slope is the rise over the run. And that is going to give me like basically the velocity. So instantaneous rate of change, I want to know the velocity at this point, right? But the problem is, in order to do a slope of that point, right? Slope is y2 minus y1 over x2 minus x1, right? And if I'm trying to find at this very instant, at that one place, I don't have a second coordinate to do y2 minus y1 over x2 minus x1, right? So here's what we do instead, right? Let's say I pick another dot on this curve, and I do a secant line instead, right? And we talked about this in the last section, in the last chapter, I think, right? If I take and find that guy, that gives me my x2, y2, right? That gives me my second point that I can do the slope of, right? But if I do the slope of this line, and that gives me the velocity, is that going to be a very good determination of that slope? No, okay? So let's do something better. Let's take and let's slide this point this direction, right? And now I'm going to do this secant line. Is that going to give me a better approximation? Yeah. Yes, but not completely, right? Let's slide that point even closer. Let's do this one instead. Is that going to give me a better approximation? Yeah. Yes. So the closer and closer I slide that dot to the actual dot, it's going to give me the instantaneous velocity of that point, right?
Just slide it like.
So let's say.
0, 1.
Right, exactly. So let's say this point is at 2, 10, I don't know, like at 2 seconds, it's 10 feet in the air, right? Okay, what I could do is I could pick out and figure out 2.01, right? And whatever that ends up being, I don't know, maybe he's at like 13 or 11 or whatever, right? Okay, I could do that and slide it so close that it will give me almost exactly the velocity, but will not give me the exact velocity, right?
What's it called the secant?
Could you find the exact
What?
velocity? Because it like has two like multiple points.
Why is it called the secant?
Secant line goes through a curve at 2 places. Tangent line only touches
Why
once.
is it
Oh
called
yeah.
I don't know. Like, why is it, like, don't even think sine, cosine, tangent, secant,
Oh,
cosecant.
it's like-
Not the same thing. Not the same thing. I don't know why.
What's the
I think they're related, but not the same.
Homophone.
What?
Zach has a question.
Yes, what?
Can we find the exact velocity?
Yes, by doing a derivative. But you don't know how to do that yet. So we're setting you up into what derivatives are, okay? Yes, I know. This is the hard part. Like 2, 1, you're going to be like, oh, why can't we just do the thing, okay? Here we go. So what we're going to end up doing is a limit. This is the bridge between limits, which is what we were doing last chapter, and derivatives, which is what we're doing this chapter, right? Okay, so here's how this works, right? So what I want to do, look at this little blue bar right here. That's what we're going to be using, okay? This little blue bar that has the definition. You guys got to listen. This little blue bar. If I have a dot here and a dot here, ready? I want to find the slope between those guys so I can approximate the slope of this one, right? Okay? So here's the deal. I want this value to approach like a very small interval. Like I want to have 2 dots that are almost on top of each other to approximate the slope. True? Okay? So what I'm going to do is I'm going to slide this x as close as I can so that the change of them is like almost nothing, right? Like it's going to approach 0, like they're on top of each other, the distance of 0, right? Okay? And then I'm going to just do the slope of them, right? Like the slope between those 2 points. Now, the distance can't be exactly 0 because then I'll have the same points on top of each other, and I can't do that. I have to have 2 separate points. Like that's how that has to work, all right? So here we go. Let's try this for example 1. It says use this definition, which is this guy right here, which is a limit, to find an equation of the tangent line, and this is my parabola that I'm dealing with. So like this curve right here, I'm going to draw a picture of him. Whoop. And I want to find, let's see, if he's x squared, he looks like this, right? He's going to smile. And I want to find the slope or the instantaneous rate of change, the equation of the tangent line at the point, this guy. I want to find the equation of this line right here, okay, at that point, right? I want to find the equation at that point, which is 1, 1. That's what I want to find, okay? And I'm going to use this definition right here to do it, okay? So we're going to start with the limit as x goes to, what? Start writing this down.
What? Oh, we can't see.
Oh, no, they can't see.
Call me George.
No, they can't see. Okay, here we go.
George Void.
I'm just writing this formula down again. Whoa. Okay. All right, rewrite that formula from up above, and we're going to start to sub stuff in. So you're going to see where this stuff comes from. Okay? Boop.
Wait, where?
Okay?
Hold on.
Yeah.
Hold on a minute.
It's really the same thing over the same.
Okay, this is this equation that I have written down, right? Okay, here's what I want to happen, right? We're going to deal with just the x coordinates for right now because limit is the y, right? I'm trying to find the y coordinate, right? Okay, so what I'm going to do is I'm going to take this x and I'm going to slide it toward the x that already exists. What x are we already existing looking at? 1 right here. I'm trying to find where that x is going to go toward, right? Okay? All right, that means x naught, the one that I'm concerned with, is going to be 1, right? I'm trying to find where he's going to go toward, okay? All right, so let's simplify some of this stuff, okay? So I have the limit as x goes to 1, okay? And now we're going to fill some stuff in. F of x is another way of saying y, right? What is the value of f of x?
1. Oh.
Right? F of x is equal to x squared, right? Now, f of 1 is going to be, if I plug 1 into f, which is 1. Do you see that? This is f of x. This is f of 1. True? And I subtract them. Yeah? Okay? On the bottom, we have x minus 1. Got it? Yeah?
Oh, we're gonna do some.
Okay, now, we're going to use our knowledge from limits the last time. Can I plug 1 in? No, because I'll end up with 0 on the bottom. But what can I do? Difference of squares. X minus 1, x plus 1, right? Okay? If I do that, I cancel that out. So now I can evaluate limit as x goes to 1 of x plus 1, which is going to be
Hold on, let me write this.
2. Okay? So we just found the limit, i.e. the derivative, right? Okay, this is another name for the derivative. What does a derivative mean? The slope of this tangent line that I have right here, right? The slope of the tangent line, this guy. Okay, if you're a little lost, it's okay. We're going to get there, okay? So we just found that the slope of this line is 2. I want to know the equation of that line, all right? How do I write the equation of a line? Y equals mx plus b. And we just found that the slope is 2, so that means what?
Y equals 2x plus b.
Y equals 2x plus b. Now,
I'm busy thinking.
I got to do one more thing,
1 equals 2.
and that is to solve for b, right? So, I'm going to plug in what?
1.
I'm going to plug in 1, 1, right? 1, 1. So, I've got 1 equals 2 plus b. So, b equals, not a half. Whoever said a half over there. Negative 1. So, the slope of my tangent line is 2x minus 1. That is the equation of my tangent line. Yes, sir.
I thought that
God, you're
you are.
Okay, what?
Oh, what am I?
The f of x is, we already know that. Isn't that
F of x is another way of saying y. So if y equals x squared, that means f of x equals x squared.
Good things come to those who
No,
wait, right?
no,
x minus
no.
whatever.
Yeah, correct. Because we're plugging 1 into x naught. That's the point that we're trying to slide toward. Okay? We want our x value to get closer and closer and closer to this coordinate of 1, right? That's what we're trying to do, is slide that point closer and closer. Yes?
Can you go to the end? Like,
I still have one more.
So this is the equation. This is the equation of our tangent line, right?
The derivative?
This is the equation of our tangent line. Yes, that's our derivative. That's the equation of the tangent line. Our derivative actually was 2.
Oh.
So if they're just asking for the derivative, 2 is our answer. We're done, right? Okay? Now, we will get to the point where you can find a derivative of this equation without actually using a limit. And that's when we get happier, right? Okay? The derivative of y equals x squared is y prime equals 2x. That's what a derivative is. Okay? Then I plug 1 in for x because that's the point I'm looking at, and the derivative is 2. So I can do this super easy without having to have a limit involved, right? But they're showing you in section 2.1, this is the bridge between limits and derivatives. Got it? Let me see if there's another example. Actually, let's go to example 2. Here we go. Let's go to example 2. Okay? We're going to do the same process again, but we're going to do it on example 2. So, what we have, I'm going to write down where we started from. The limit as x goes to x naught of f of x minus f of x naught over x minus x naught. And that's what we're going to do for right now. Yeah. Okay? We want the equation of the tangent
Let me
line.
write this down.
Okay, write that down. That's where you're going to start from every time. Because this is going to tell me the what? If I evaluate this limit, that tells me the derivative, which equals the slope
Of the tan line.
of my tangent line, right? Okay? So that's going to give me the m. And then eventually what I need to do is get y equals mx plus b. And this will tell me the m, right? Okay? So that's what I have so far. Okay? Good, good? So what we're trying to do is we're trying to find the equation of this line. They give you the answer. Shh, listen. They give you the answer. What's the answer?
Negative 2/4.
Right here. Negative 1/2 x plus 2. That's what we're trying to get to, right? Okay? So I have given you the answer of what this problem eventually will end up being, right? Okay? We want to find the answer of where this guy touches at 2, 1, and I want to find the tangent line of that, right? So this is the point 2, 1. Okay? So let's fill in our limit formula. We want the limit as x is approaching what? 2, right? Okay? And we've got f of x. What is f of x? What are we going to plug in for f of x? 2 over x. Oh, because the x coordinate that we're looking at is 2. Yes, good question. Okay. Minus f of x naught. So if I plug my x naught value, which was 2 in, right? If I plug it into here, it will be 1, right? Over x minus 2. Yeah? Okay. All right. Now we got to figure out what we're going to do with this, right? Can we plug 2 in?
Over X.
Can we plug in 2?
Now, why is 2
No.
over X?
What?
Where'd you get
Up
the?
top,
That's
why
our
is 2
equation.
over X?
That's our equation.
Correct. That's what that is.
What? Where'd you get the 2?
What are you confused about?
I just
What's
asked
the
that
equation?
question. It says y equals it.
Right here, right. The point 2, 1. So our x is approaching a an x coordinate of 2.
Y goes on top and X goes on bottom.
Yes.
Because that's where we got the negative
Funk
1 and
uncle?
the 2.
That's where we got the what?
The 1 and the 2 from on the right.
Probably
No.
true, probably true.
No. This one is f of x naught. If x naught is 2, right? If x naught is 2, we're going to plug 2 into our f function, right? I plug 2 in here. And 2 divided by 2 is 1.
Okay, so
Okay?
since y equals
X
2
naught
over
is
X,
just 2.
Since y equals 2 over x, f of x is just y,
That's
so...
what it equals.
Correct,
in that.
correct, correct, correct. Yeah? You're fine, you're fine. Okay. All right, so we know we can't plug in 2. Let's see if we can do some other stuff. I don't like... Hold on. I don't like fractions on the top. Let's do this. Let's get a common denominator. Listen, real quick. Let's get a common denominator. So let's make this x over x. Let's see if this helps us. I have no idea if it's gonna. Let's see if it does, right? Okay? So if I make that x over x, then this guy on top is gonna be 2 minus x over x minus 2 over 1, right?
Right.
You see how I just made that into a fraction? Yeah, yeah, yeah. Okay? Okay, okay. All right, good. Yes? Okay?
Oh,
All right. Now what?
Now you
I
multiply
looked
by
away
X
for
plus
1
2,
second
get 'em out of the
before we
box.
get
Now I'm going to multiply by 1 over x minus 2. Okay? You see what I'm doing?
Yeah.
Okay, now we have a problem. I really want to cancel this and this out, but I can't.
Why is it 1 over x minus 2 and not x plus
That's
2?
what's gonna happen like that, cause it ain't no. Wait, why
Say this again.
Why is it
What
1
part is
over,
you can-
why is it 1 over x minus 2 instead of x plus 2 over 1?
We're multiplying by the reciprocal.
Oh,
Instead of
reciprocal.
dividing by a fraction, we're multiplying by the
Oh,
reciprocal.
we're reciprocal.
Yeah,
Why did we do the x over x in the first
Because
place?
I want 2 over x minus 1. I want to get a common denominator so I can put them together and write them under one roof. That's why I did that. Okay? All right, are we good so far? Hold on. Just wait. Are we good so far?
Yeah.
No?
Yeah.
Keep going.
Do you want me to back up?
Nope, keep going.
Okay, so we're multiplying by the reciprocal here on top, right? Okay, I really want to cancel these 2 out, right? But I cannot. So what I'm going to do is I'm going to pull a negative 1 out, and if I do that, that's x minus 2. True?
Yeah.
Do you see how that works? Don't.
Cross
No.
them out.
I
Okay,
guess it's
come on.
weaker.
So it's negative 1 over X.
Now I can cancel these 2 out, yeah?
Yeah.
So now I have negative 1 over x, yes? And I'm doing the limit as x approaches what number?
2.
2. Okay. So now can I plug 2 in? Negative 1/2. And that is the what?
Over it.
That is the what?
The limit.
The limit, which is the derivative, which is the
Cool thing.
slope of my tangent line. So now I have y equals mx plus b, and I know that the m is negative 1/2. Is that what they have in my graph?
Okay, so what did we cancel out the x minus 2 with?
Oh, holy moly!
Ring.
Shit.
Because you wasted all of our time.
I did, I'm sorry.
Kobe, we have cross country tomorrow.
Yeah, that's
Okay. All right, did you get where we got, Remington? Okay.
Yeah, I see. We canceled it out with the top thing.
Yeah, so that's my m. All right, we will begin again tomorrow.
Confusing.
That is confusing. It is.
Megan,
It is
what'd
a
you
little
do in
bit.
civics?
Okay.